In this section, we're going to look at learn how to do some division of algebraic expressions, and just like we did with multiplication, we're going to start simple and then move to more complicated scenarios. So if there's no addition or subtraction happening in the numerator or denominator, we already know how to do this problem. We're going to use the rules of exponents. So in this first example, we've got 3x to the 8 divided by x cubed. The rules of exponents tell me I can subtract those exponents, and we get 3x to the 5th. Similarly here, I've got, there's no addition or subtraction, so I'm just going to work on using the rules of exponents, and sometimes we can make things a little bit easier for ourselves if we just sort of organize. I'm writing it this way just to make it more apparent how I need to approach this. So we've got, to begin with, negative 6 over 2 is a negative 3. S squared over s to the first is s. The t's just cancel. And then I've got z squared over z to the 4th. Now I could think of using the rules of exponents and to subtract those exponents and get z to the negative 2, at which point I just have to stop myself and say, okay, I don't want to use negative exponents, so I'm going to throw that in the bottom. The other way to think of this part is to say I've got z squared over z squared times z squared, so that you can cancel one of those, and then you see that that definitely belongs in the bottom. Similar situation here, only 8 doesn't go perfectly into 18. I'm going to do some, I'm going to rewrite this, I think, in hopefully a helpful way. So we have up top 2 times 9, a cubed times b to the 6. Now notice that I've got a b squared in the bottom, so I'm going to write that as b squared times b to the 4th. Down in the bottom I have negative 2 times 4. A to the 5th I'm going to write as a cubed times a squared times b squared. Now I kind of chose to split up these products in helpful ways so I could just think of it as canceling common factors. You could also go about it by using the rules of exponents. That's you'll get the same result either way. So overall, up top I have a 9b to the 4th. On the bottom I have 4a squared, but note that it's also negative. So overall this fraction is negative. And so I've got 9b to the 4th over 4a squared. If your result is negative, it's conventional to put it either out in front of the fraction, as I have written it here, or with the numerator. It's not common to leave the negative in the denominator. Okay, so our next scenario is, what if we have some addition and subtraction, but just in the numerator, so not in the bottom? So you might remember that if we have to add fractions, that if we have a common denominator, we just bring that denominator over, right? And then perform the operation, in this case, the way it's written here, addition on the numerators. But this fact works in both directions. So if I think about going the other way, what this says is, if I have addition happening up top, and the same is true for subtraction, but here if I have addition happening up top, I can split up that fraction and just perform that operation here between the two fractions. So if I have addition in the top, addition or subtraction in the top but not the bottom, that's how we're going to approach it. We're just going to split it up. And then once we've split up that fraction, we can approach each of the resulting fractions like we did on the last examples. So this is 4a squared over 2a plus 8a over 2a. Now I'm just going to reduce each of these. 2 goes into 4 twice, a goes into a squared, cancels with one of those factors of a, so that first fraction reduces to 2a, and 2 goes into 8 4 times, the a's cancel, and this last term is 4. Next we're going to start this one the same way. I've got addition and subtraction in the top but not the bottom, so I'm going to make three different fractions: 4x cubed y over 2x squared y minus 8x cubed y squared over 2x squared y plus 2x squared y over 2x squared y. I'm going to reduce each of these fractions. So 2 goes into 4 twice. The x squared cancels, leaving us with just x to the first, and then those y's cancel. So this first fraction reduces to, 2 goes into 4 twice, reduces to 2x. Bringing down the minus here. 2 goes into 8 4 times. X squared cancels, leaving us with just x to the first. Y cancels, leaving us with y to the first. So we have 4xy. And in the last fraction, you might notice everything cancels. And when everything cancels, it doesn't leave us with nothing. It doesn't leave us with 0. It leaves us with 1. All right, now we're going to look at another scenario. And before we get to dividing, when we might have addition or subtraction in the denominator, this division that we're going to do is for kind of specific situations, and it involves dividing polynomials specifically. So a polynomial is an expression that deals with just positive integer powers on your variable. That's basically it, right? So there can be no square root of x, there can be no 1 over x, right? Just positive integer powers, and then, you know, some coefficient on each of the terms. So in this next example, we're just going to figure out what is a polynomial and what is not. If something is a polynomial, what is its degree, meaning what is the highest power that appears on x in that polynomial? So in part A, this is a polynomial. I only have positive integer powers on x. It is degree 3. In part B, that is a polynomial of degree 7. In part C here, this is not a polynomial because of that square root of x. We know that that's x to the 1/2 power. So that means it's not just positive integer powers on x. This is not a polynomial. In part D, also not a polynomial because I've got an x to the 5th, but it's in the bottom. So I know that's really an x to the -5. Polynomials have positive integer powers, so this is not a polynomial. Now, the process that we're going to use to divide two polynomials is similar to the long division that you may have learned back in, elementary school or middle school. And so I wanted to start just by doing a long division of numbers problem, because how we approach the polynomials will be completely analogous to this. So if I want to take 533 divided by 4, the first thing I do is I just pay attention just to this first digit, 5. So 4 goes into 5 once. I put the 1 up here, and then I multiply. 1 times 4 is 4, and we subtract. 5 minus 4 is 1, and I bring down just the next digit here. And then I start over. 4 goes into 13 3 times. 3 times 4 is 12. I subtract. I get 1. I bring down the next digit. 4 goes into 13 3 times. 3 times 4 is 12. I subtract, and I get 1. Now, what we do from this point can vary depending on if we are looking for a decimal approximation or not. But I'm going to avoid decimals right now and say, okay, I've got this remainder of 1. And what that means, the way I interpret this result, that I got a 133 up here and a remainder of 1, is that 533 divided by 4 is equal to 133. So I take that quotient up there, and 1/4. Now normally when we say and 1/4, we would write it as a mixed number like 133 and a quarter, and it's fine to write it that way. But when we say 133 and a quarter, it really means that we're adding them together, and I want us to remember that because that will be important when we do this long division with polynomials. So let's do one. Let's say we're going to divide these two polynomials, 6x squared plus x minus 2. I'm going to divide that by 2x minus 1. So I'm going to set it up like a long division problem. And I'm going to pay attention first just to the first two terms, right? The first term in each of these expressions. So I've got the 6x squared and the 2x. I ask myself, what do I multiply by 2x to get 6x squared? And that is 3x. So I take the 3x now and I multiply it by the whole divisor. So when I do that, I'm going to get 6x squared minus 3x. And just like when we did long division with numbers, my next move is to subtract. But I have to subtract the whole thing, so I'm putting parentheses. That's kind of important. I have to make sure. It's really easy to make sign errors here. So 6x squared minus 6x squared, that goes away. That is by design. That first term should always just cancel. And next I have x minus a negative 3x. So that's x plus 3x or 4x. And now I bring down the rest of the terms. There's only one term remaining, but generally what I do is I bring down all the rest of the terms. Now I start the process over. What do I multiply by 2x to get 4x? And that's 2. It's a positive 2, so that means the next term in my quotient is plus 2. And then I take this 2 now and I multiply that by the divisor. So we get 4x minus 2, and then we're going to subtract. Now I can see that we're taking 4x minus 2 and subtracting itself, and that does naturally give us 0. So we got a remainder of 0. That means that 2x minus 1 is a factor of 6x squared plus x minus 2. What we would say as a result is that 6x squared plus x minus 2 divided by 2x minus 1 is equal to 3x plus 2, and that is absolutely correct. You can check, because the multiplication way, the other way to write this relationship is that 3x plus 2 times 2x minus 1 is equal to 6x squared plus x minus 2, and we could do a quick check here. So let's see, that's 6x squared minus 3x plus 4x minus 2, which is 6x squared plus x minus 2. And that does in fact check out. Next, got one more here, 4x cubed plus 6x squared plus 1 divided by 2x minus 1. Okay, so let's set this up as a long division problem again. 4x cubed plus 6x squared. Now watch what I'm going to do here. There's no x term up there, so I'm going to put one in. I don't want to change what the expression is equal to. I just kind of want a placeholder. So I'm going to say plus 0x plus 1. Now you don't have to do that, but I find that it's helpful. It helps me avoid errors. And I'm dividing this by 2x minus 1. So I start the way we started before. What do I multiply by 2x to get 4x cubed? And that is 2x squared. Now I multiply this by the divisor, so I get 4x cubed minus 2x squared. I'm going to subtract the whole thing. 4x cubed minus 4x cubed, those cancel. 6x squared minus a negative 2x squared is a positive 8x squared. Now I'm bringing down the rest of the terms, plus 0x plus 1. Now I start over. What do I multiply by 2x to get 8x squared? That is 4x, a positive 4x, so my next term is plus 4x. I take that 4x, I multiply by the divisor, I get 8x squared minus 4x. Now right here, this is why I put in that plus 0x in the middle. When I'm doing the subtraction, it's really nice and convenient that my like terms kind of sit on top of each other. And without that 0x, I wouldn't have that. So having the like terms sitting on top of each other, kind of stacked with each other, helps me avoid errors. So 8x squared minus 8x squared, that's 0, those cancel out. 0x minus a negative 4x is a positive 4x plus 1. And then we start over again. What do I multiply by 2x to get 4x? That's 2, positive 2, so my next term is plus 2. And then I multiply. 2 times 2x minus 1 is 4x minus 2. I subtract. The 4x's cancel. 1 minus a negative 2 is a positive 3. So this time we did not get a remainder of 0. And by the way, I know that I'm done because when I did the subtraction, I had the degree of this polynomial, that's degree 0 because there's no x's, is less than this degree right here. That's a degree 1 in our divisor. So as soon as I get to the point where there's more x's in the divisor than there are down here after you do the subtraction, that's when you know that you're done this sort of algorithm of division. So I got a remainder of 3. So what that means is that when I do this division, I get first my quotient, 2x squared plus 4x plus 2, and then plus, you take your remainder, put it over your divisor, plus 3 over 2x minus 1. And that is the result.